hello, welcome back to our channel. Today we are going to discuss about the electromagnetic induction. It is also very simple chapter, and don't leave this chapter for mains, NEET as usual for MSET also. Okay, so in this chapter, previous chapter, you know that moving charges and magnetism. Charge at rest condition can able to produce only electric field, and charge at moving condition can able to produce both electric and magnetic fields. But you know that when the charge is in moving condition, it can able to produce the magnetic field around it. Later they were thinking, is there any possibility the magnetic field can able to produce the electric field? Then they have done many experiments, and finally they have given the clarification, yes, it is possible. With the help of the magnetic flux, with the help of the magnetic induction, we can able to produce the electric field and induced current and electromotive force and all these things. So this is the main concept from this chapter. Before that, we are starting with magnetic flux. What is magnetic flux? Generally you can say that the number of magnetic lines of force pass, you feel these four lines are there, magnetic lines of force passing through the area, and perpendicular to the area is called the magnetic flux. While writing the expression, we can say that magnetic flux is represented by phi b equals to b bar dot a bar. B is the magnetic induction and A is the area. It should be right BA cos theta also. But always you remember that theta is the angle between angle between B bar and normal to surface area. Generally what we are thinking, this is the angle between B and A. No, it's not, it's wrong. So it is the angle between normal to the surface area and magnetic induction. See, what is the unit for magnetic flux? You can say that Weber or Maxwell also we can take it. Then we are going through the another formula, that is the Faraday's Law of Electromagnetic Induction. The first person who given that and who did that experiment, reverse of that moving charges and magnetism, is the Faraday's Law of Electromagnetic Induction. From this, suppose you are taking one coil is here. Here magnetic flux, we can write it BA cos theta also. N is the number of turns, theta is, you know, the angle, and B is the magnetic induction, A is the area of the coil. Then when we are coming to Faraday's Law of Electromagnetic Induction, he said that electromotive force is equals to negative rate of magnetic flux. Means the rate of change of magnetic flux is producing what? Electromotive force. This is called the induced electromotive force also. Now we can take it E equals to minus d by dt of, instead of magnetic flux we can take it BA cos theta. BA cos theta, if number of turns are N, we can take it BAN cos theta. Here there are different applications. Look here, if B is variable means remaining all we can take as a constant. So E equals to minus AN cos theta. We can do that dB by dt, otherwise it should be right B1 minus B2 by T1 minus T2 also we can take it. Like that we can find out the electromotive force when B is variable. Like that, if A is variable means remaining all are constant, you can write it phi b equals to ABN cos theta within brackets A1 minus A2 by delta T or T, you can take it. Like that, based on that variables and constants, we can change this formula. This is the basic formula for induced electromotive force and magnetic flux relation. This is the Faraday's Law of Electromagnetic Induction. Later they focused on, yes, he said that change in magnetic flux is giving the electromotive force, induced electromotive force. Because of that, the current is developed, that is called the induced current. Then they focused on the what are the directions of this one. It was introduced by Lenz, that's why this is called the Lenz law. See, he took one coil here, one magnet is here. This is the north pole and this is the south pole. When it is moving towards this, it behaves like a north pole and the direction of the current is anti-clockwise direction. Same coil, but you see the direction of this movement of the magnet moving away from this. Now it behaves like a south pole. The direction of the current is like clockwise direction. Suppose you are taking one more magnet, instead of north pole we are taking south pole, and this one, when it is moving towards this one, it behaves like a south pole. This is like clockwise direction. Like that we are taking south and north pole, but it is moving away from this, means this coil, it behaves like a north pole. Now the direction of the current is like anti-clockwise direction, we can take it. So it was given by the Lenz's law. Not only this one, if we are taking one coil, actually the coil is like this, we have to place and we should drop one magnet here. The magnet is coming like this. See, we are dropping one magnet here. Then what happens? Magnetic force is acting upwards, then weight is acting downwards. If both are in equilibrium, we can say that F equals to mg. Suppose it is coming downwards, then what we are taking? Resultant force equals to mg minus magnetic force. Then here, acceleration of that one is how much? G minus F by m. So when you know the G value on earth is 9.8 meter per second square, magnetic force suppose that is 20 newtons and mass is the 2 kgs, means you can find out the acceleration of that given magnet. Look here, suppose F equals to 20 newtons, m equals to 10 kgs. Then A equals to how much? A equals to G value approximately 10 minus 20 by 10 is the 2, so 8 meter per second square. Like that we can able to find out the acceleration. So this is about the Lenz's law. Then we are focusing on motional electromotive force. From the motional electromotive force, see, this is one of the short answer also. In the case of motional electromotive force, we can take it one frame. Length of the frame is motional electromotive force. We are taking one frame. Length of the frame is the L. This is, we are taking, we have to move this one towards and this one. We are placing this is in uniform magnetic field of induction is how much? P bar. Then here you remember that electromotive force is B into L bar cross V bar. With the help of the cross product you can find out, and it should be right BLV sin theta also. BLV sin theta. If theta equals to 90 degrees here, you can get it. Electromotive force is how much? BLV. When you know the electric force, we can able to find out the current also. From the Ohm's law, we can write it I equals to E by R. So we should write it BLV by R. This is the current. When you know the current, we can able to find out the charge also. Instead of I, what we are writing? dq by dt equals to BLV by R we are taking. So this is that. Then we know that on the conductor how much force is acting? B into I into L. So B into, instead of I, what we are writing? BLV by R into L, means you can write it B square BL square BL square V by R. When you know the magnetic force, you can find out the power also. Power equals to force into velocity. Here B square also we are getting B into B. B square L square V square by R. So you must remember all these formulas, then you can able to find out the induced electromotive force. This is the electric current. When you know the resistance, this is the charge and this is the force and this is the power. All belongs to induced condition only. So this is about the motional electromotive force. Suppose one rod is rotating in uniform magnetic field, then how to take that formulas here? See, we can take it. One rod we are taking, length of the rod is the L, that is rotating in the uniform magnetic field, that is rotating in the uniform magnetic field. Then how much electromotive force is acting? We can take this one, look here. See, if the rod is rotating in uniform magnetic field, this magnetic induction we are taking V bar, and this is the rod. Length of the rod is how much? L. So in this case, half B L square V we are L square omega. In terms of linear velocity also we can write it half into B into L square into, this is the V by L. Radius is nothing but R. After that, half B LV also we are taking. You remember this formula, then easily you can able to find out the electromotive force. If you want to do, we do one problem also. This is 4 Tesla, length is like 1 meter, velocity is 2 meters per second. Then how to find out the electromotive force? Half into 4 into, length is 1 and this is the 2. After simplification, 4 volts we are getting. 4 volts we are getting. Then next thing we are going to discuss about self-inductance. What is the self-inductance? It is the property of the inductor. It opposes the flow of growth and decay, growth or decay of the current. That is called the inductance. So that device is called the inductor. In the case of inductor, self-inductance means in this only we are using one switch and one coil is there, and along with galvanometer. When you open or closing that key, then what happens? Current is flowing through this. That is called the induced current. That is called the induced current. And here you should write it. This electromotive force is directly proportional to electric current. So E equals to what we are getting? One constant. This is called what? This is called the self-inductance. But E equals to d phi by dt. We know that E equals to d phi by dt also we are taking. Otherwise, first we are taking magnetic flux. Phi is directly proportional to current, then phi equals to L into I. And here L is the self-inductance. This is the self-inductance. And unit is what? Unit is the Henry. Unit is the Henry. So instead of, but from this you can able to find out the electromotive force. E equals to minus d phi by dt. But instead of d phi, what we are writing? L into I. L into I. So E equals to L into di by dt. See, two formulas are there. For finding the electromotive force in terms of the self-inductance and current we can use. For finding the magnetic flux we can use this one. This is about the self-inductance. Then there are different cases. We are taking the self-inductance L1, L2, inductors like L3, all are connected in series. What is the resultant? This one, L equals to L1 plus L2 plus L3, like that. If these are connected in parallel, so at that time we can take it L1, L2 means L equals to L1, L2 by L1 plus L2. If n number of inductors are there, means 1 by L equals to 1 by L1 plus 1 by L2 plus 1 by L3, so on we can take it. So this is completely belongs to the self-inductance. And one more formula you should remember here, that is the energy stored in the inductor. E equals to half into L into I square. L is the self-inductance, I is the current, like this. Then we are getting the mutual inductance. Mutual inductance means we have to use two coils. Mutual inductance, we can use the two coils. In this case, magnetic flux in the secondary coil is directly proportional to current in the primary coil. So instead of proportionality constant, proportionality symbol, we are getting one constant. That only we can say mutual inductance, and the current in the primary coil we can get. Then based on this electromotive force, d phi s by dt. Then instead of phi s we are writing mutual inductance into Ip. So E equals to M into dIp by dt. This is about the mutual inductance. Not only this one, we can find out the relation between mutual inductance and self-inductance also. See, we are taking two self-inductors and we are placing like that. This is the L1 and this is the L2. Here m square equals to, we can take it L1, L2, then m equals to under root L1, L2. So directly we can use, suppose L1 equals to 4 Henry and L2 equals to 16 Henry. Then how to find out the mutual inductance? You remember that mutual inductance is also having the same unit, Henry only. So under root 64, we can write it 8 Henry. Like that we can able to find out the mutual inductance of the coil. Then we are going to discuss about last thing is the AC generator. AC generator, you should remember that E equals to E naught into sine omega t. Based on this AC generator is works. Anyway, this is coming in the alternating current also. So this is very small chapter. First thing you have to remember that what is the magnetic flux. Then Faraday's law of electromagnetic induction. We are getting the relation between electromotive force and magnetic flux. Otherwise, the rate of change of magnetic flux is directly proportional to the electromotive force. There, instead of magnetic flux, we have used BAN cos theta. Depends on that variable and constant, and depends on the situation. We can use that formula in different ways. You can use. Then motional electromotive force and motion of the rod in the rotation of that rod in the magnetic field. Then self-inductance and inductors are in series and inductors are in parallel. Then mutual inductance, relation between the self-inductance and mutual inductance. Thank you everyone. Please subscribe my channel and share my channel to your friends also.